compress it, and moreover, from this then compressed matrix product state form, I showed some ideas how we can bring it into the so-called canonical form that then allows us to conveniently evaluate local expectation values, but also correlation functions and the like. But this still leaves out the following problem, and this is maybe kind of what we are usually facing, is that we might be interested in the ground state of a specific Hamiltonian. We not necessarily have a friend with a huge computer that can do this calculation for us. So what we actually need are some tools that find in this kind of search space or in this manifold of matrix product states or an approximation of the ground state that we're interested in, right? So I hope that with this discussion that we had, I convinced you that the class of Hamiltonians that we're interested in, we would find a solution in this subspace or in this this manifold of matrix product states, but we don't know yet how to find it. And this is what I want to discuss now. So for now, I want to assume that we have a Hamiltonian that is strictly short range, so it has only coupling between nearest neighboring sites. Right? Examples of this Hamiltonian would be maybe the Hubbard model, or Heisenberg model, and Ising model, and so on. So, and what I want to show you is now some algorithm that can do two things. So first, it will actually allow us to perform time evolution in real time. So let's say that we have a Hamiltonian, have a state given as a certain time, and we just perform a real-time evolution of a state to get us to some time t. And moreover, once we know how to simulate the time evolution of a state, we can switch to imaginary time, and from this find the ground state wave function, right? So if you just start from some arbitrary wave function that has some overlap with our ground state wave function, then we can just apply to it the imaginary time evolution operator, and that will project out all excited states and leave behind just the lowest energy state. Right? So this is now what we want to do. So there are now a few steps involved. So the first one is that since our Hamiltonian has this specific form, we can trotterize it, which means we can now split the terms into two parts. We can now decompose the Hamiltonian H into some F plus G, where F are now terms that act only on even bonds, right? So here we have the F terms, and we have the G terms. The G terms act only on odd bonds. And clearly we see that all F terms mutually commute because they don't have any terms in common. And also all terms G commute because also they don't have any operators in common. So they act only on different sides. However, we see that G and F do not commute because, for example, this G and this F here, they overlap here, and which means that if we have maybe some X operator here and a Z operator here, then they would not commute. But this gives us to the so-called Suzuki trotter decomposition, because now what we can basically do is, like, if we have our time evolution operator, like with a full Hamiltonian, like F plus G, we can then actually approximate it in certain orders. So in the first order, we just write it as X times Y, which basically means that this is just the product of e to the I delta t times F times the I delta t times G. And then we can also go to higher orders, etc. And by this reduce the error that we make in delta t, right? So we just assume that we just make a time evolution by a small step delta t, and then we can perform this with some error that is delta t squared per step here and delta t cubed per step here. And if we do this decomposition, then we actually have have something that we already find quite easy to write down, because now, as I pointed out, all the terms f commute, which means that the time evolution operator for f's can be just simply written as a product on all even bonds of the time evolution operator for a bond, and the same for G, right? So, and each of those gates, so each of those terms acts only locally on two adjacent spins or sides. So what we have now boiled down, we have now boiled down the problem to time-evolved states to something rather simple, right? So now using this convenient graphical notation again, we have now a matrix product state, like this is the guy written up here, at a given time t. And we want to perform now the time evolution in this trotterized form, right? So now we just have a product of all those gates f's first, right? So this is just only acting on the even bonds, and in this graphical notation, this just amounts to having to multiply these unitaries u to these to two adjacent matrices here, here, and here, and so on and so forth. And the next step, in the next trotter step, or the second part of the trotter step, we will then actually have to do the same on the odd bonds. But from this kind of picture, we see that all we need is actually an algorithm that actually starts from a given matrix product state at a given time, applies these matrices U, and compresses it or kind of converts it back to this form that we had before. Right? The moment that we have this kind of algorithm, we actually know exactly how to do the time evolution, because once we arrived here, we can actually just go back and then would do the update on the odd bonds. And then using this trotterization, just by alternating an update between even bonds and odd bonds, we can then perform the both real-time and imaginary time evolution. Right? So the question is, how do we get from this form back to our canonical MPS representation? And this is done by the so-called TBD algorithm that was introduced by Gifle Vidal a couple of years ago. And the idea is now it's relatively simple. So we first go to the two sites where we want to perform an update and contract all the matrices shown here to a new representation theta as given here. But let me just elaborate a little bit what that means, what we have done. Because having this form is a quite nice representation of the wave function. Right? So recall that when we have our matrix product state of this form, so we have alpha, lambda, gamma, lambda. Now we have some index alpha here, and index beta here, and I here, and j here. And this is now our theta, gamma, alpha, j. And this is now actually a representation of a wave function in terms of Schmidt states to the left of side I, Schmidt states beta to the right, and local states I and j here. Right? So basically this is now a representation of our wave function I, j, alpha, I, j, beta. Right? So basically, by contracting these guys together, we actually have now a representation of a wave function in a mixed basis where we use both Schmidt states and local states on this side. And if we have now kind of transformed our wave function into this basis, then we can actually just apply our unitary gate to this object and contract it, which means we're just summing over all these indices, and that leaves us now with a transformed wave function. So this is now the wave function where we applied this one Trotter gate to it. And by this, on this bond locally, we just kind of changed the entanglement on this bond, right? And we already applied it. But what we want to do now is we want actually to go back from this kind of form to this canonical form that we had before. And we are now using exactly the same trick as before, as we did when we will perform a Schmidt decomposition or a singular value decomposition of this object. So we're now just performing a Schmidt decomposition at this middle bond, giving us now the new Schmidt values, because these Schmidt values actually have likely changed by this unitary, and the new kind of unitaries to the left and to the right. And from these, we can now directly extract the transformed tensors gamma B and gamma C here, right? So if we just perform this, we can actually perform the exact time evolution of our state. But this comes at a cost. And we see this in the following way. Let us now assume that we just initiated our state with a simple matrix product state where on each bond we have a bond dimension of chi. Because each of these bonds has indices from 1 through chi. Then this blob, or this object here, has then a bond dimension of chi, d, and chi, like d being the physical dimension. But when we perform a singular value decomposition of this object, which is done here, then the bond dimension here has actually increased from chi to d times chi, right? Because this is a d times chi cross d times chi dimensional matrix, and if you perform a singular value decomposition, then we have actually d times chi singular values. But that's bad news, because at each time we apply a layer of these Trotter gates, we actually would find that the bond dimension increases by a factor of d, which means it increases exponentially. And the way to overcome this is that at this point, we actually perform a truncation. Right? So we have exactly the same picture as what we have here. We just have now some Schmidt values that have increased to a certain amount. And then we're just saying that, okay, all the Schmidt values that are smaller than, say, 10 to the minus 10, we just neglect. And we hope that we've chosen the truncation kind of good enough, or like made the truncation error small enough, such that the physical observables you are interested in are not affected.
Sorry?
Yes?
You said we increased the bond dimension, but the two bottom legs of X and Y are less frequent. What would you do contracted with that?
Which one's the one on the left and the right?
Yeah.
Exactly, but the as I showed earlier, so we have now the, if this is now our spin chain, we now perform first updates on these bonds here, right? So which means that then the bond dimension increases on this particular bond from chi to d times chi, and on this bond. But on the next level, like when we apply the Trotter gates on, say, the odd bonds, we will increase the bond dimension here. So we just increase the bond dimension alternatingly on the even and the odd bonds. Does this answer your question? Good. Yeah, and with this fairly simple algorithm, you will also play in the afternoon in the tutorial session. Because this is actually, if you use Python, you can just implement these few steps in a few lines of Python, and you have now then a code that allows you to both perform the real-time evolution and imaginary time evolution in this with matrix product states. Good. So far we now assume that the system is it's like a finite system, say, where we have L sites. But there's a quite simple and neat way to directly apply this method in the thermodynamic limit. And for this, let's assume that if we're starting from a state that is translation invariant with a particular unit cell, so we have AB, 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 and we are performing exactly this kind of algorithm, right? So we would first do an update here. We do then an update here, then an update here, and so on. And if we have this translation invariant state, after maybe doing this update for 5, 10, or 100 times, you will realize that each time you're doing exactly the same thing, right? So each time you are starting from some two-side MPS that you contracted, you just apply the same unitary, and you just perform the same SVD, right? So each time you're doing exactly the same thing. But then you might think that, well, instead of redoing this SVD over and over again, you could just say that, well, let's assume that we have done all the AB updates in parallel, and that's it, right? So you just basically do the update once on a bond AB. And in the next time step, you just do an update on a one BA. And you can forget about everything else here. So you just basically store two matrices. So you store two of these rank 3 tensors, and you just alternatively do an update on the bond AB, and then on BA, AB, BA, and then you can directly simulate the system in the thermodynamic limit, just by doing it this way. Good.
Sorry, in that case, what do you do? How do you deal with the boundary conditions in that case?
Well, in this case, you don't have a boundary.
Yeah, but effectively, you still have left and right indices to your MPS, right?
Yes. Yeah, so it's literally like this. So if I just take this form here, at the first update, you just have here, say, A, B, B, and this is like a B, right? You just contract these guys, get now the new gamma A, new lambda A, new gamma B, and the lambda B have not changed, right? So let me just put then, after you perform the step, you have then the tildes here, and now you just, and then you just do the update the other way around. Then you choose your gamma, lambda B, gamma B, lambda B tilde, gamma B tilde. Is it the right way? Or no, sorry, like this is, these ones are tilde, this is not tilde. Right, and then you do an update on this guy. So you just really swap AB, AB at each step. And then the idea behind this is that you're just sort of a million times doing the update in parallel on A bonds and B bonds. And then you just don't have to worry about these boundary conditions.
Is this not a sort of periodic boundary condition?
Was it?
Is this not like periodic boundary?
No, it's not. Because if you had, because
at each iteration is.
No, it's not, because if there's actually a subtle difference. So let's assume that I have my system, like if I have a system with a unit cell of, I don't know, 4 sites, then if I'm doing a singular value decomposition, then at each step, I just basically have like some orthogonal basis alpha to the left and an orthogonal basis beta to the right. If, however, I think of the system on with periodic boundary conditions and I form a Schmidt decomposition, then the system is not actually cut into 2 halves, because the Schmidt states alpha and beta, they actually would have some overlap. So this setup does not correspond to periodic boundary conditions, but to infinite boundary conditions. If I wanted to do the same algorithm with periodic boundary conditions, I could do this too, but then I would have to use a different way to update the last site. I mean, there's a way using swap gates, but I mean, this is getting a bit trickier.
Okay, I asked simply because you are contracting on the first and last one of the same index.
Yes.
So from this point of view, it looks like a very boundary condition.
Yes, so the update, like when applying these gates, this is the same as, like at a given step, the multiplication of this unitary. This is as if it were with periodic boundary conditions, but the way that we are doing this Schmidt decomposition and assuming that the Schmidt states, this is a step that makes the difference between infinite and periodic boundary conditions.
In the TBD, you discriminate between even and odd boundaries.
Yes.
But physically, there is no distinction between them, right?
That's correct.
So you don't have a way to do it only once instead of twice in two types of bonds?
Not that I know of, I mean, because basically you're using this Trotter decomposition into A and B bonds, and that even though the physical Hamiltonian does not break the translation symmetry, this kind of Trotterization does. And there's no easy way, I'm not aware of any way how you can do this this TBD algorithm by not artificially breaking the translation symmetry. There are other algorithms, like the ones that I'm showing in a minute, that actually allows you to, that you don't have to do this, but for the TBD algorithm, you would have to do it. Good. Let me now come to some second algorithm that I briefly want to introduce, and this is a so-called density matrix renormalization group. So, and this density matrix renormalization group algorithm has a number of advantages. So first of all, it's actually significantly faster than the TBD algorithm in finding ground states. And secondly, it is not limited to Hamiltonians that have just nearest neighbor interactions, right? Because this TBD algorithm, because of its Trotterization, explicitly assumes that the MPS, that the Hamiltonian has the form that it just couples nearest neighbors, and this density matrix renormalization group method does not. But it's conceptually like slightly more complicated, although closely related. So for understanding this kind of formulation of the density matrix renormalization group method, actually I need to introduce one other concept, and this is the so-called concept of matrix product operators. So probably after hearing about them for several times now, you're already very familiar with the concept of expanding states in terms of matrix product states, where we get these kind of expressions. But now assume that you have an operator acting on that Hilbert space. You can actually expand it in terms of matrix product operators, which means you actually have now just one more leg basically sticking out of these guys. And these are now, at least conceptually, any operator acting on your Hilbert space can be expanded in a product of those matrix product operators. And once you have this matrix product operator, you can then apply it to a given state. And the way that you're applying it to a state is that you're just contracting all these lines in the way that we discussed earlier on, right? So this could be psi, and this could be the Hamiltonian, and h times psi is now something that you get by just contracting all those matrices together, and you're done. Well, similar, we can now calculate expectation values of operators, right? Previously, we discussed in detail how to calculate expectation values of operators. That's for local operators, but we can also have operators that are not so local, like operators that couple various sites. And again, we can just write it in this kind of sandwich now. So this is psi, we apply h to it, and then we just have the conjugate of psi. Good. And the question is, how can we find these matrix product operators? And I just want to demonstrate it for a concrete model. Let us say that we have some generic operator that is coupling, say, nearest neighbor sites, as the one here, but it could be whatever you like. What this actually means, like if we have an operator like this, then it actually means in this kind of compact notation that we have some operator A acting on the first bin with tensor dot with some operator acting on side B, tensor dot with identity everywhere else, plus identity on the first side, AB, identity on anything else, and so on and so forth. So this is actually what we want to express now. And without commenting too much on this, I want to say that there's then a very compact way of expressing this in terms of so-called matrix product operators. And for those that you are interested in this, I can actually tell more about it during the lunch break. But the idea is that we can construct so-called finite state machines that construct all the terms in a given Hamiltonian. The finite state machines are known from engineering. If you have maybe some setup, how you want to operate some machines, you're there in certain states, they're doing something, and then there's some event happening, they're doing something else, and they're going through a certain cycle. And this is like the same that you can construct Hamiltonians. You could say that, well, be first in a so-called ready state and always put identities until you go to the kind of intermediate state by putting some A operator. Once you have put the A operator, you know all you can do is to put a B operator and go into the final state. And in the final state, you keep putting identities. Right? So this is basically the sort of finite state machine for constructing these Hamiltonians. And without much explanation, I just state that every finite state machine can be written in this kind of matrix form. And then we actually have now a very compact way how we can write down many of the Hamiltonians that we might be interested in. So that's good, because now we can write down an algorithm that actually variationally minimizes the energy. Right? And for this is, well, I just showed you that we are all very familiar with matrix product state, so we just guess whatever ground state we might have by just writing some guess in terms of the matrices A. We now know how to express our Hamiltonian in terms of the this matrix product operator, and we just sandwich it with the conjugate of this wave function, and this is now the energy expectation value. And now we can basically just minimize this, so we can just basically take out one of the matrices, and this gives us now, assuming this canonical form, a representation of the Hamiltonian in terms of our orthogonal states. And then we can use some standard method like Lanczos or Jacobi-Davidson to actually minimize or to find the ground state of this effective Hamiltonian projected into this space of kind of Schmidt states. And again, if you have this sort of variational minimization of the energy, then it's actually much faster than than the TBD algorithm, and it actually allows for long-range interactions. And if we have this particular form, it also allows us to have real translation invariance, I mean, to the question earlier on, because here we don't have to explicitly break the symmetry. And the algorithm that we then derive from this is conceptually quite similar to what we had before. So we contract all the matrices around, say, two sides or one side, depending on how we want to do the update. Then we have now our wave function given in a mixed representation. Right? So this is exactly the form that we had in this TBD algorithm. Now we minimize the Hamiltonian. So this is now the effective Hamiltonian. We just use some standard tools for finding the ground state of this effective Hamiltonian. And now we have some new kind of updated wave function, which again we bring back to the canonical form, and we just start over. So then we move to the next site or bond, depending on how we do the update, right? So now this is an algorithm similar to what we had before, where basically the bond dimension increased, so we would have to do some truncation at this step again. So this gives us the DMRG algorithm. So let me now give some comments on these algorithms. So first of all, the algorithms that I basically sketched here can, when being implemented, be made much faster by using different conserved quantities. So for example, if you have like a Hamiltonian that conserves the particle number or conserves the total magnetization, this can be explicitly conserved in the construction, and by this we can make these algorithms significantly faster. Well, one trick and is if we actually have if we're just using this algorithm directly in the thermodynamic limit, then we actually can use this transfer matrix that we have encountered before, like when we were constructing this canonical form. Then we know that the dominant eigenvector of this transfer matrix is the identity because of the canonical form, because of the Schmidt states are orthogonal. But the second largest eigenvalue is directly related to the longest correlation length in the system. So this is a quite handy tool if we, for example, want to look at critical points where we know that the correlation length will actually diverge. And this gives us one way, as I said, and this is a slide where I want to just take a little bit of time to explain it. We could now say about the following. Let's say that we have now some Hamiltonian, in this case, for example, the transverse field Ising model, and then we know that for a small transverse field, we are in a gapped phase where we have a ferromagnet, and for large G, we are, for example, in a gapped phase where we have like a paramagnet. And now you recall that I was pointing out that the algorithm and these ideas work in gapped phases. But in between, there's a critical point where the system is gapless. So we actually cannot write down the ground state exactly as or we cannot write it in a very good efficient way in terms of a matrix product state. And this is now sketched here. So let us now assume, so if we plot here the correlation length of a system as function of the transverse field. And now at the critical point, the correlation length will diverge. So we have like an infinite correlation length. But let us now obtain the correlation length from the matrix product state, from these matrix product state algorithms. So what we will find is the following. If we are staying far away from the critical point, we will actually recover practically the exact state because the truncation that we perform is very small, and we just get exactly the correct correlation length. And the same is true if we just stay deep in the other phase. But as we approach the critical point, the correlation length is getting longer, and thus we actually would need a larger and larger bond dimension or more and more states to accurately describe the state. And this is now shown here. If we have like a small bond dimension, very quickly, like maybe here, the correlation length that the optimized MPS has is actually different from the actual physical correlation length. And if you increase the bond dimension, we actually get a better approximation. And in fact, if we just look at how this scales, we can actually learn something about the universality of this critical point. Good. So this concludes the first part of what I wanted to talk about, which was sort of an overview of how entanglement, or like how specific entanglement properties of these one-dimensional and gapped local Hamiltonians can be used to to efficiently, or to show us that we can efficiently simulate these states, these systems using matrix product states. And I discussed two algorithms, namely the time-dependent block decimation and the density matrix normalization group, as two algorithms that allow us to work in this manifold of matrix product states to find good approximations of ground states. Well, I guess I will get started on the second part after the coffee break, but maybe that leaves us some time for questions that you might have.
Practical question. So how large are for example, on the laptop, how large are the systems you can investigate? Don't do the infinite setup.
Well, I mean, how large in terms of the bond dimension?
For example, and of physical size.
But the physical size, if it's infinite, right? So if you just use this translation variant, I mean, that's just to stress this again. I mean, if you have a translation invariant system, as here, you only would need to store two matrices, like two tensors. So in that, because you just know that the system is translation invariant, that's all that you need to describe the infinite system. And the only kind of question that remains is like how large of the bond dimension can you simulate on a system, on a computer?
For GMRG, you need really a finite.
No. DMRG, you can also apply, the same idea that I gave before about using translation invariant state, you can also use in the MPS setup. So that works both for TBD and, so it's exactly the same idea. So you just, when you're doing these updates, here you would just have, instead of having ABC here, you would actually just have lambda B and just replace it by the same one.
I think you went very fast over the DMRG algorithm.
Yes.
Can you just slowly repeat that part?
Well, I mean, no, the thing is that, I mean, I realized that this was too fast to kind of understand all the details. I just wanted to give you the main idea. And the main idea is really that instead of doing imaginary time evolution, which we did for TBD, the main idea is to actually variationally minimize the energy. You say that, well, you actually know how to calculate the energy for a given matrix product state, and now you have some ways to minimize this energy. So this is the main idea, and then I just sketched very quickly the point of how to actually do this minimization, but before implementing it, you might want to read some lecture notes. Yeah. Actually, we'll come into this later on, but there are some lecture notes that I will refer to. So.
So you start by saying that you're interested in area law states and
Uh-huh.
want to represent them efficiently.
Yes.
Is there proof that all area law states can be represented by MPS with finite bond dimensions?
Yeah, so there's a proof if you prove that, or if you have states where there's an area law for so-called Renyi entropies with an index kind of smaller than 1, then there's a proof that those states can be represented efficiently in terms of MPS. There's one more in the back. Oh, you mean how to implement these charge degrees of freedom? Oops. Yes? Uh-huh. Right. So here the idea is the following. I mean, it's maybe also easiest explained if you just do a Schmidt decomposition, say. So if you, well, if you perform, let me just think about it. right? Or even like if you just have the state, right? If you have like a state defined on I1 through IL, and now you just do a bipartition of a system into some parts, and now you say that the total number of charges is conserved, right? So then you can have a quantum number n left and a quantum number n right. And you know at every given time that n left plus n right is equal to your particle number, which is conserved, which tells you that in this representation of the wave function, if you have now, I don't know, some basis I here and a basis j here, and you just write down the wave functions in I and j, that this will be block diagonal, right? Because you have only non-zero contributions in this wave function whenever like n left I plus n right j is equal to, say, the total particle number. And this block structure is something that you can then use for accelerating these codes. Yeah?
If a system has a certain symmetry, can it be used to optimize the code in any way?
To have symmetries.
Yes. If a system has a symmetry, can the code be changed so that it needs to do less iterations? Or?
Right, I mean, the way that you can improve it is by basically reducing the kind of the space in which you have to do the optimization, right? So if you, I mean, this is like basically just boiling down to this, what I answered to the previous question, that if you have certain symmetries, so for example, particle number conservation, you know that a wave function in this form would have would be block diagonal. So when you perform any contractions of these tensors, then you actually know that there will be zeros here and here, so you just don't have to iterate over those. So that makes it faster.